Hello there.
Sometimes creating an ad campaign can feel like you're talking on mute.
Sorry, we can't hear you. Say that again?
But advertising on Spotify can help your business turn up the volume. With our easy-to-use ads manager, you can create new audio ads from scratch or repurpose existing video assets. Then we'll deliver your ad to an engaged audience that is ready to hear and see your message. It's that simple. Learn how Spotify can add more to your mix at ads.spotify.com.
Good evening and welcome everybody, this is Obi-Wan Pez for Simplex Pachinko. We are doing some math education review tonight, so looking down through a few papers that we might see and see if anything's particularly useful. So this one is arXiv from 21st November. Mathematics, Rise of the Machines by Yang-Hui, London Institute for Mathematical Sciences, Royal Institution, University of Oxford. We argue how AI can assist mathematics in three ways: theorem proving, conjecture formulation, and language processing. Inspired by initial experiments in geometry and theoretical physics in 2017, we summarize how this emerging field has grown over the past years and how various machine learning algorithms can help with pattern detection across disciplines in the mathematical sciences. At the heart of the question, how does AI help with theoretical discovery, and what are the implications for future of mathematics? Invited contribution to the New arXiv for Viscount of the Koninklijk Wiskundig Genootschap, based on the recent public lecture of the author to the Royal Institution of Great Britain. I believe this is too tall. In a sec. Nope. Okay. Whether you are of the opinion that artificial intelligence is a threat to humanity or the opposite belief that it is mere hype, it cannot be denied that, whatever its precise definition, AI is already transforming our daily lives in almost every respect. I know that Angela Collier would probably have something to say about that. Oh, there it is.
Looking for black tie?
Nope. In case you haven't seen it, that is a link for Angela Collier's video on YouTube entitled "AI Does Not Exist But Will Ruin Everything Anyway." Essentially, as it says on the tin, the idea here is that AI literally does not exist yet. There is no current AI in any respect, although some of them might look like AI, they're still not. It is, in most cases, not even like Mass Effect, a virtual intelligence or VI system. I am also of the mind that we should probably move toward the Mass Effect classification of virtual intelligence being those things that are not actually intelligent, but like, you know, efficient computer systems that can help you look up stuff. And then synthetic intelligence being those things that are actually genuinely intelligent, which again, we don't have any of those yet. Even though AI has a much older history than many would imagine, a formidable combination of compute, your mobile phone outpowering the entire lunar program, and the internet, essentially all of human knowledge at your fingertips, has galvanized this transformative impact in the last 2 decades. The word artificial intelligence was first coined in a grant proposal in 1956 by McCarthy et al. Shortly thereafter, the perceptron, after the first artificial neural network, or ANN, was established as an impressive array of photoreceptors and wires. So, as a reminder, right, I have done some work with neural networks. Doesn't have to be like this, but actually. Right, we could, in fact, do something much more like this. Okay, so typically there's going to be something that looks sort of like this, where we have x sub I, where that could be our input. Yeah. We have what's called a hidden layer. And then we have the output layers, or output layer. So typically a neural network looks something like this. All of the individual all of the individual weights are going to be given at any particular location. Sorry, we get a little extra happiness in the throat today. We'll see something that looks, roughly speaking, like this. We have the input layer, again, at the front, which is where all of our inputs go. It could be literally anything you want, like any number of these things. The hidden layers are just connected to the input layers and then connected to further hidden layers, potentially, up until the last hidden layer, at which point those are connected to the output layer, which can be a single node. It can be an array that is larger than what you started with. So it depends on what you want. What are you getting for input? What do you need for output? One that I did was we dealt with a RGB network. So it was just going to be like, you know, what are the RGB values in this picture? Then when we did that, there were a whole bunch of hidden layers in the middle. I don't even remember if I picked a specific number or and then on the output it was also RGB. I believe the idea was that you would input the RGB value for that particular pixel, and then you would calculate the RGB values. What was it? Actually, I don't think that's true. I think I calculated the RGB value that we're on, the RGB values of every point like immediately surrounding it, and then it started using those at a lower and lower weight as you went out, and then it would be influenced by all these other ones, and then it would end up putting one particular value down, and then, or like move every pixel within range, within the effective range, closer to its particular value. So the ones that were right next to it were almost the exact same value that it was. They moved like 99% of the way. And then as we move out, the distance affected how much it would be turned toward that particular color. So this was to model the predator-prey scavenger example that we had in partial differential equations. So again, use the particular value it landed on, calculate what it should do to the points around it, and then use a distance function to pull everything toward its color. This was done effectively like a random sampling, I think. I think if it were actually going to be a good neural network, it would have done would have been a little bit more continuous. I don't know exactly how I would have done it, but it wouldn't have looked quite the same. And as cool as it was. And depending on what colors were present, if there were too many predators, then they would end up dying off, and then the scavengers would end up coming to prominence because now the predators are dying off, and they've already eaten pretty much all the prey, so they start dying off. The scavengers come to prominence because that now there are large quantities of food available to them, i.e. other dead animals. And each of them had a particular partial differential equation which represented how they would affect one another. So, the population of a particular species by itself will end up with a logistic function that goes kind of like this. Kind of starts at a very low value, increases exponentially, and then starts decreasing toward an exponential asymptote on the top. It's not quite exponential, but it's close enough. And then when we look at the interaction between species, this then affects what else is going on. So the size of the prey species population will end up causing the predators to also increase, and then also will cause the scavengers to increase, because now again there are more dead animals laying around, so they're able to get in there. The presence of the scavengers, I don't think I actually affected the other two at all. But again, if there were too many scavengers, then they would eventually eat everything that was there and just go away. And then also the herbivores ended up coming to prominence in those sections, and then the scavengers would come back, and then the predators would come back. So it was a very interesting example. So the single perceptron is going to have weights that come from particular inputs. All right, X sub I. These will be H sub J, so and then we have weights that also connect to W J sub K. Will connect to outputs Y sub K. And in fact, really, we don't need to talk about the inputs and outputs by themselves. We're talking mostly about just what's happening with the individual perceptron. So yeah, there are inputs X sub I, there are outputs Y sub K, but we don't need to worry about it too much. We really want to focus on the stuff that's in the middle. So any one node, we can look at it and say, okay, this is a perceptron, and again, like was discussed, right, the perceptron is the first artificial neural network. While I shall leave the question of influence on AI on our civilization to the experts in AI research, to sociologists and to philosophers, it is my goal here to give a rapid overview of the emergent but blossoming field for AI for mathematics. To be fair, both mathematics and theoretical physics for AI and AI for experimental sciences have been long distinguished histories. For instance, the early universal approximation theorems that ensure good estimations from neural networks, or the Boltzmann machine as an energy-based model for cognition, date to the late 1980s. So too did CERN's first usage of machine learning for detecting fundamental particles. The 2024 Nobel Prize in Physics to Hinton and Hopfield, and in chemistry to Hassabis and Jumper, is proof of the establishment's timely recognition of the role of AI in scientific discovery. Pure mathematics and theoretical physics, by the very nature of rigor, may seem unlikely companions to the big data and statistical inferences inherent to AI. Yet I will describe here how in 3 ways AI will be a positive driving force for mathematical research: bottom-up, top-down, and meta-mathematics. Admittedly, these 3 words have various precise meanings in the philosophy of mathematics and in the philosophy of science. I beg the reader's indulgence for borrowing them loosely, as I shall define them in the ensuing. The interested reader is referred to the following for more information and in-depth reviews. Right, bottom-up mathematics. Typically, one thinks of mathematics as an austere 3-step process, laying out axioms, definitions, terms, and concepts with precision. 2, claiming a statement involving the terms, and 3, using logic to deduce the statement. Since Euclid's immortal tome, The Elements, woo, shout out to The Elements, this is how mathematics is always presented. Classic example, Proposition 20 of Book 9 is as follows. 1. Definition. A prime number is a positive integer which is only divisible by 1 and itself. 2. Proposition. There is an infinite number of such prime numbers. 3. Proof given below. Footnote. This bottom-up presentation of statements in mathematics, building sentence by sentence from the foundational definitions and axioms, perhaps reached its zenith with the publication of Principia Mathematica in 1910. With a sparsity of words, a plethora of symbols, and an inhuman coldness, the monumental work was famously able to reach 1 + 1 = 2 on page 362. Even though its entire programming of formalizing mathematics was in part killed by Gödel, Church, Turing, with their showing the existence of undecidable and uncomputable statements, researchers were not deterred in using the earliest version of the computer, the logical theory machine, to formalize and prove a number of propositions in Principia. This was almost immediately after the appearance of the first neural network. Likewise, the idea of mechanized mathematics dates to that time. Today's answer to that tradition is to this tradition of bottom-up mathematics is the automated proof assistant. Notably, MATLib, built in the Lean programming language, launched in 2013. Project Xena has completed the formalization in Lean of statements and proofs of essentially all undergraduate level mathematics. Nice. Equally impressive is the fact that formalizing whilst doing collaborations has already led to major results by the top mathematicians. As proof co-pilots are becoming the norm for mathematical research, it should be emphasized that so far there are no large-scale AI involved in MATLib. The main challenge here is one of engineering. There is only on the order of millions of lines of Lean, whereas currently reliable language models, which I shall turn to later, typically require billions of lines to train. It is conceivable that in the not-too-distant future, we will reach auto-formalization, which will take all journal papers in LaTeX and generate verifiable Lean code for the whole corpus. Already, DeepMind's AlphaGeo 2 and AlphaProof have Lean incorporated into their core algorithms. Once accurate auto-formalization is achieved, it may no longer be a fantasy that proof paths may be found using reinforcement learning for open major problems. Right. We're gonna get up. Because my goodness. Righto. Dost thou ihn hoist? Hope everybody's having a good Tuesday. Nope. Still Monday. It even says so right at the top of my screen. Monday, 8th December. Oh, man. All right. Right out. Top-down mathematics. Lest the reader be led to think that mathematical research is always done in this formal and rather stark bottom-up way, I must point out that in practice the opposite is the case. To quote the great V. Arnold, mathematics is a branch of physics where the experiments are cheap. Indeed, even rigorous proofs are formulated first by some gut feeling, as summarized in this wonderful article by Thurston. Certainly, theoretical physics, the closest cousin between theory and experiment, is the standard model of particle physics. But we still do not have a precise definition of the underlying quantum field theory. This fearless bravado is the very reason why string theory has produced so many new insights in pure mathematics. The idea of experimental mathematics is as old as logic and reasoning. It is how the practitioner actually does theoretical research. We play around, trying to get intuition, and then formulate the right definitions and proofs before finally writing up the papers more formally. In today's parlance, this might be called data-driven mathematics, where one builds experience by finding patterns in a broad understanding of the research landscape, looking at the subject from top down. After all, in the beautiful words of G.H. Hardy, a mathematician, like a painter or a poet, is a maker of dreams. If his patterns are more permanent than theirs, it is because they're made with ideas. Mathematical data is distinctly different from data from the natural world. It is without statistical error and often represented by integers rather than reals, whence also has no freedom for numerical error. These have been dubbed Platonic data, whose machine learning can uncover underlying mathematical structures. Continuing with our example of prime numbers, one of the highlights of this data-driven mathematics was the 16-year-old Gauss defining the prime counting function. Pi of x is approximate. I don't remember exactly what that one is. Oh, shoot.
You create new audio ads from scratch or repurpose existing video assets. Then we'll connect your ad to an engaged audience that is ready to hear and see your message. It's that simple.
Is defined as. Okay, cool. So pi of x is defined as the number p prime such that p is less than or equal to x, which is a positive real number. The number of primes not exceeding a positive real x. He was able to eyeball that pi of x is approximately x over natural log of x, and the proof had to wait some 50 years, especially for the development of complex analysis, before it was established as the prime number theorem, one of the cornerstones of modern mathematics. Based on the experience and intuition, Gauss formulated a conjecture by looking at the Platonic data, whereby establishing a good problem. In some sense, bottom-up mathematics can be thought of as finding proofs, and top-down mathematics as finding interesting problems. One needs to bear in mind that 2 of the remaining 6 millennia problems, the Riemann hypothesis and Birch-Swinnerton-Dyer conjecture, BSD conjecture, arose from mathematical experimentation by listing the first zeros or by plotting rank and conductor. Starting from the late 1980s, attempts were made to automate the process of formulating conjectures in combinatorics, which in 2017 took the updated form as Tix Graffiti. In the same year, the first AI-assisted mathematical experiments were performed, where datasets from algebraic geometry were passed through a neural network in order to uncover potential new structures. Therein, calculations in algebraic geometry, and later, all mathematical calculations in one way or another, were interpreted as image processing. So too did 2017 see machine learning applied to mathematical physics in exploring the string theory landscape. Since then, the field of AI for mathematical discovery from Platonic data quickly blossomed and matured. Hundreds of papers emerged, with notable successes including Ramanujan machine in finding identities for famous constants, the finding of new formulae in topology and representation theory, as well as the machine learning discovery of the still open murmuration conjectures in number theory. Three, metamathematics. Finally, I come to perhaps the most mysterious direction in which AI can galvanize mathematical research. Let's see. Sorry, I'm looking at the connection for my standing desk. Hasn't been plugged in since I got to England, but now might be a good time. Ooh, sorry. This is a world of large language models, LLMs, ChatGPT, Gemini, I believe that's supposed to be Google's Gemini, Grok, DeepSeek, etc. It may seem peculiar that chatbots, famous for their hallucinations, could be of any use to mathematicians or mathematics. Indeed, though they have, over the last couple of years, rapidly outperformed and replaced humans in myriads of tasks, LLMs struggle even in doing basic arithmetic, because, as we discussed in Zach's stream, I believe, they are essentially guessing machines. Okay, question. Is it pulling on anything? Yes. But 31.6, where does that put me? Not high enough. Yeah. See how this goes. Cool. And then we just twist this a little bit. Alright, that should do it. So, double check, and move a little forward. Alright. Language models rely entirely on statistical inferencing, whereas mathematics requires reasoning. Bottom-up is rigorous by construction. Top-down's conjectures can be disproven rigorously. What can vague sentences and potential word salads do for mathematical discovery? We'll come back to that in just a minute. Tanziru, good evening and welcome. Irrelevant question, not at all. Most of my entire most of my channel is based on the idea that we should be, helping out students. So, as always. Right. How can we draw x equals 1, y equals 2, x equals 0, y equals 2? So, are these points, individual points, or are they 4 separate lines? They are 4 separate lines. Okay. So, if...
But how can you move on when everyone's still talking about it? Under the Bridge has stunned critics. It's a true crime drama where a writer and cop investigate a murder tied to troubled teens. The Guardian says Riley Keough and Lily Gladstone are superb.
With no sloppiness. Make our axes like this.
Others get everyone talking. Under the Bridge, now on ITVX.
Sometimes, creating an ad campaign can feel like you're talking on mute. But advertising on Spotify is different. We'll help your business turn up the volume and reach an engaged audience that's ready to hear and see.
So, if we're looking at 4 separate lines, and so from here we want to look at these axes and go, okay, this is going to be -1, -2, -3. This is going to be 1, 2, 3, 4, give or take, right? 1, 2, 3. -1, -2, -3. Right. So the point here is that we're trying to find for x equals, I suppose, for something that says x equals 1, we want to find all of the possible locations where the x value is 1. So as we come over here, we know that this is going to be the x direction, and this is going to be the y direction, as is standard. So, if that's what we want, then what we're going to do is say, okay, we want all of the individual points where the x value is 1. So the x value is 1 here, and also here, and also here, and 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 here. I think you probably get the point, though, is that at all of these values, we see x values that are all 1s, right? So this point right here is going to be 1, 0. This point here is going to be 1, -2, etc. Right? So if we have, literally in this case, an infinite number of points that could very well end up being an infinite number of points that could have this x value of 1, then we don't have to put in all the individual points. There are so many, like I said, an infinite number, that we could actually put in just a line and say, hey, this is going to be what we've got. No, that's not what I want. Ah. Oh, you jerks. Apparently I have just crashed the website. Okay, there we go. No. Okay, so apparently I needed to just hit escape. And of course... Okay, so that's why I asked. So as long as the x value is 1, it is literally every single y value. So 1 comma y. Whatever your y value is, those points are all going to make this line. So for x equals 1, again, really all of these individual points are going to be 1 comma whatever you feel like. And really it's not that point, it's any point is going to be given by this. So yeah, go all the way up here to 1 comma 3, put that in. And in fact, let's take this and move it over here. And then let's take this entire thing and move it away from the junk that I wrote up there. Oh, that's fun. All right, so that's the first one. Now your second one was y equals 2. So if we change color, all right, and do y equals 2, this says, similarly, if our y value is set at 2, then our x value can be, well, anything. It doesn't matter what x is as long as y is 2. So this one right here is going to be -1, -2. This one over here is going to be 3, 2, not negative. -1, +2. This one over here is 3, 2. We could do something in the middle here like 1.5, comma 2. Right? Any particular x value that you want, as long as y is 2, that's all that's been defined. So you're going to get all of these points. Whenever y is equal to 2, x could be literally anything again. Just like with the other one. How do we get 3? I made it up. Right? Because these were defined individually, you said. That x equals 1 is its own line. Y equals 2 is its own line. Now, if I have misinterpreted, there is one other possibility. And that is that the actual question is...
When your kid's favourite toy starts to run out of battery power, no need to worry. Your new batteries are already on their way, arriving today with Amazon Prime. Everyday essentials delivered fast. It's on Prime.
I'm Professor Huggington, and I like to hug.
Cut-off times and T's and C's apply. See product page when ordering.
And it might be something that looks like this. Now, I'm not sure entirely, but obviously you have the paper. So there's multiple possibilities here. The one that you said was that there should be separate lines. So, like I said, there should be 4 separate lines that we make. If, on the other hand, let the rectangular region in the z-plane, aha, yes, okay. That's also slightly different, but we'll deal with that in a minute. Okay. So as boundary conditions, right, what we're seeing now is that there's going to be this horizontal line here, which is stroke up, sloppiness up. Okay, so we've got x equals 1, y equals 2. Next one was x equals 0. So again, in this case, every value where x is 0, but we don't care about what the y value is. So again, here this is going to be 0, 3. This is going to be 0, 1. This is going to be 0, negative 1.5. So the other important part of this is that we don't actually care about these individual points. These are just points that exist on that line. So we're going to use them, but we don't actually necessarily care about those lines by themselves. So we go like this. We say, okay, we're going to cover all of those lines. It's going to go like this. That is x equals 0. Again, x is 0, don't care about y. Y is not particularly defined in that equation, right? X equals 0. So it is just all of those points along this line here. Right? Every single point. Infinite number of them. And then, that's going to be a bit of a problem. So you have 2 lines. Yes, x equals 0 is the y-axis. Y equals 0 is the x-axis. Now I think that you made a typo. One of your y's should probably be y equals 1 or y equals 2 or y equals... one of them is y equals 2. I think the other one should be y equals 0 or y equals 1 or y equals negative 1 or something like that. And if you could just double check, because otherwise we've got just a line. That doesn't really work. Y equals 1 and y equals 2. Yep, okay. And x equals 0, x equals 2. Cool. Oh. So y equals 1 and y equals 0? Okay. So that's going to change things a little bit, but honestly not that much. So if we go through like this, we take all these individual, all these individual points and just move them down. All we need to do is change these 2's to 1's now. Oop. Right. We need that green back. That one. Y equals 1. 1, 1, and 1. And that belongs down here. This 2 doesn't belong here. Should just be a 1. That could be 2. Okay. Then that means that we have another value here at y equals 0. Again, same deal. So the reason we can say it's supposed to be these values here are, these are all the points, again, where our y value is equal to 0. Okay, so if we line all those up, x equals 2. That was the other backwards bit. That's perfectly fine. Oh no. Okay, so x equals 2. Yep. Alright, good enough. Yep. No worries. So your rectangular. Now this is in the XY plane, so there's one other thing that technically needs to be done about it. Right? This is your rectangle. It's a terrible color for this. We liven it up a bit? No? Okay. Make it whiter. See it a little bit easier on the other background. Yeah, no worries. Now, like I said, there is one other concern here, is that this rectangle is in the XY plane. If you want it on the Z plane, the Z plane runs this way.
Can feel like you're talking on mute.
Sorry, we can't hear you. Say that again.
Which is to say it's inside, or it runs from like out here into the board. So this is a third dimension thing, right? It's going to go this way. So if it is in the z-plane, that means that this region also continues with it as a prism. In both dimensions. Now, or in that dimension, in the z direction. If that is not what your teacher meant, or if that's not what the book meant, then they maybe need to clarify that a little bit more. Didn't show you three-dimensional stuff? Okay, then ignore that. We'll just ignore that. So it is in the XY plane. Nice. Okay. Well, anyway. Yeah. If they didn't show you 3D stuff, then don't worry about it. You just say, you know, this is going to be the rectangle that we need. It's in the XY plane. Then you go from there and do whatever calculations you need. Okay. We're going to take a 3-minute ad break. I'm going to untangle the stuff that is underneath my desk. And I will see you all back here in 3 minutes. So thank you very much for coming. And if anybody has more mathy type questions, please ask. I will be here. So see you in 3 minutes.
You know the drill. End of series, credits roll, the next ITVX show begins. But how can you move on when everyone's still talking about it? Under the Bridge has stunned critics. It's a true crime drama where a writer and cop investigate a murder tied to troubled teens. The Guardian says Riley Keough and Lily Gladstone are superb, while AV Club calls it gripping and devastating. Some shows end at the credits. Others get everyone talking. Stream Under the Bridge now on ITVX.
With the festive season approaching, the last thing you want to be thinking about is energy prices. Thankfully, our next pledge tariff future-proofs your energy with cap-beating prices. So whether the cap goes up or down, you're still winning. To find out more about Next Pledge, visit eonnext.com/save. Next Pledge is a 12-month fixed
All right.
tariff with
And we're back.
standard variable tariffs.
Okay, so I have raised the desk back to like a normal height. Oh my god. My HOTAS is going on the blink like you wouldn't believe. So I may be learning the Elite Dangerous method of flying by keyboard and mouse a lot quicker than anticipated. Really hope not. Okay. So we have So, what can vague sentences and potential word salads do for mathematical discovery? Very good question, because I'm sure we all, those of us who have ever worked with neural networks and or ever tried to work with either auto proof solvers, Lean, for example, or anything like that. Curiously, in this direction, extraordinary advances are being made. I will call this direction meta, since we could well be outside the mathematical reasoning and depend solely on AI having linguistically seen essentially all of mathematical literature. From the first and rather naive word-to-vec analyses of the arXiv in order to uncover theories from language, to the now much more sophisticated LLMMA2 to Vrol 2023 Llama. One should not underestimate the power of proof by vibe. I cannot tell you how like almost physically ill any sort of like, oh yeah, vibe coding or proof by vibe, like any of that is starting to make me. An AI which has read all of the contemporary mathematics and can be queried at will is a force to be reckoned with. There is an increasing number of reports from mathematicians who, upon interacting with the likes of ChatGPT-5, have discovered useful literature of which they were not aware, or are instantly presented with ready-made computer code that turn out to be useful in testing ideas. Meanwhile, LLMs can now attain a gold medal in the International Mathematics Olympiad by training on the language of previous solutions. All of this is happening in the last couple of years. In May this year, some 30 of us were flown to headquarters of Epoch AI to help benchmark FrontierMath, a project funded by OpenAI to see how various LLM models solve research-level mathematics, the sorts of problems that one would work on and write papers about. Accuracies of 10 to 30% have been achieved. And the consensus was that oftentimes it truly felt like talking to an experienced colleague. The few hundred questions were divided into tiers from undergraduate level to publishable results. Samples and performance statistics can be seen at the anticipated tier 5 would involve open conjectures and problems, and the frightening thing is that we are not too far off from that. Trace the triangle t of the w plane into which t is mapped. Under the transformations given, I minus, oh boy, 1 minus I times z plus 2I, triangle t in z plane with vertices at I, 1 minus I, and 1 plus I. Interesting. Hey Zach, how's it going? And a greetings and salutations to you as well. So, 10-0, I think I'm slightly bothered by the wording of it just because it may be a slightly different translation-ish, or the way in which you all do your mathematics just has a slightly different setup. So whenever I hear plane, I need to know which two variables that plane is covering. So there's going to be one direction this way, one direction that way, or they could be skew, I don't really care. But there are going to be two lines. In the case of our Cartesian coordinates, it is x and y, so that gets us the x, the x plane like runs this way. The y plane would run this way. And then our z plane would run like in and out of the if we're saying that z is just equal to 0 or a single constant, then like the z plane is this one right here. Okay. It might work. So, typically when I'm seeing this, these are going to be real and imaginary axes. So, right, it's going to look like this. One minus I is going to be here. Or this would be 1 minus 1 or 1 minus I, depending on how you want to write it. All three of these are technically valid. It's just a different way of operating with all of them. Okay, and then 1 plus I is going to be here. And then I. So this would be 0 comma I, for example. And then you want the triangle that runs between all three of these. Right, so that's T. So, Do you know what to do from here?
Hey, is your old phone giving you a hard time? Why don't you swing by Sex and upgrade today? It's easier on the wallet, better for the planet, and with a giant 5-year warranty, you'll be grinning to... Hey, I'm recording an ad here. Get out of the way. Sex, everywhere. Online at weebly.com or search CEX.
When your deodorant has been reduced to a tiny whisper and tries to tell you, I'm running on empty.
How's the night been going, Zach? I noticed Stuki was on doing some final writing of paper, I believe, or something like that. Or like final checks on all results. Seems exciting. Having never published, I wouldn't know. Oh. Been working on stuff. Nice. Ooh, nice. The pachinko board will rotate. Awesome. So, Tanziro, do you see where to go? Oh, okay, there we go. Complex number will cause rotation. Nice. Right, so what I would probably assume is going to happen, because I'm sure I've done this problem at some point, but not quite in the same context. What you should probably want here is that, like, if you have points A, B, C like this, well, let's do, like, call it P for point. You take your old point, P, which is going to be one of these three values that you've got, A, B, and C. You plug that value, which is a complex number, in for really it's the Z, which was what was given there. I think probably they want it to be, that'll work. I hesitate to do this because I don't want to get you the indication we're doing like calculus or anything, but right, this particular prime means different. Same, but different. So what you want to do is plug each of those points, A, B, and C, as the vertices of your triangle into Z over in that equation that you typed out. Then do all of the multiplication and adding that you need to, and that's going to get you Z prime, which is the different one. So either A prime or B prime or C prime. Hey Famished, how's it going? And then when you plot those on your real imaginary, right, plot the new ones, A prime, B prime, C prime, then you'll get a new triangle. You probably want to show that as T prime, wherever that is in the plane. I have no idea where, but yep. So take each of your expressions for them, I plus 1, I minus 1, plug them in for z, do your multiplication, and then add 2i. So you got to do 3 different calculations, but, you know, should be easy enough. Finish up programming courses. Nice. You got to test your skills for algebra. Yep. Yep. See you soon. Yep, we were just talking about mathematics, the rise of the machines. This was talking a little bit about Epoch and OpenAI. Well, OpenAI is Epoch. Word2Vec and Llama, which are all essentially vibe proofers. We talked a little bit about Lean way back up there, and Project Xena. So, yeah, this one got me here. Zach, you'll like this. Accuracies of 10 to 30% have been achieved. And I mean, if it is actually solving research level mathematics at an accuracy of 10 to 30%, that's maybe not too bad. If it was, you know, solving known calculus at 10 to 30%, that might be a problem. I don't know what they've exactly included in that, but I would assume that is going to be, yeah, that's not that's not clickable. That's slightly annoying. Wish it was. Again, a few hundred questions were divided into tiers from undergraduate, tier 1, to publishable results, tier 4. Samples and performance statistics can be seen below. Okay, so let's take that as well. The anticipated tier 5 would involve open conjectures and problems, and the frightening thing is we're not too far from this. Okay, outlook. In concrete mathematics, Graham Knuth and Patashnik made the half-jocund remark that, quote, the ultimate goal of mathematics is to eliminate any need for intelligent thought. What they meant was perhaps all methods of proof and derivation will be mechanized in the infinite limit of mathematical research. At the time, in the late 1990s, it was deemed outlandish that such mechanization would ever be possible, and yet the combination of human and AI in the last decade has given us AI for maths, propelling us into a new era of fundamental theoretical discovery. Like AlphaZero effectively solving Go, mathematics too can be gamified. Of course, we're still quite far off from a mechanized AI for mathematics that can follow an automated path of 1. Find new problems from Platonic data and existing literature. 2. Find verifiable proof paths using vastly extended versions of MathLib. And 3. Check the significance of the statement within the global and historical context. Seeing that ChatGPT passed the Turing test, okay. I think that deserves a giant asterisk on that one, but we'll see. And that the AI community is working hard in the ARC test, benchmark for AGI reasoning. A more stringent test was proposed for AI-assisted mathematical discovery, named after Birch of the BSD conjecture, whose online talk inspired the participants of a conference at Cambridge in 2024. The Birch test can be summarized as AI-N at AI. An AI-guided mathematical discovery needs to be automatic in that human intervention is forbidden in choosing data, literature, and algorithm. Interpretable, in that any statement must be meaningful to an expert, e.g., having a deep neural network that extrapolates an output without understanding the underlying mathematics is useless. And non-trivial, in that any conjecture raised must be significant to the scientific community. While arguably only the Jones polynomial formula and murmuration conjectures and finding unstable singularities for the Euler equation have come close to it, the Birch test is so far unsurpassed. Nevertheless, with the advent of AlphaEvolve, mathematical exploration and discovery are now at scale. It should be noted there are 67 problems selected for study, which are of particular nature, finding upper and lower bounds or numerical counterexamples, which are particularly amenable to optimization and code-oriented searches. Mathematics of the near future is clearly a joint effort between human expertise and AI's prowess in all three directions: bottom-up, top-down, metamathematics. Even in a hypothetical distant future where complete mechanization is achieved, where AI will disprove or prove every major conjecture and propose new problems and continuously map out new areas of research, human mathematicians are still of great value. We will simply become priests to oracles and interpret the results to the rest of humanity. Think of the philosophy departments of the world. Centuries are spent in analyzing and critiquing Plato, or the literature departments over Shakespeare. Perhaps one day in the far future, mathematics departments will consist of experts digesting the MathLib verified proofs that AI produces. Still, I think a number of my colleagues agree with the exclamation HLF. The exclamation that I don't care whether it is God, AI, or Terry Tao who finds the proof of the Riemann hypothesis. I just want to know. I am grateful to Ananyo Bhattacharya, Thomas Fink, Thomas Hodgkinson, Roman Rybyansky of London Institute for Mathematical Sciences for their invaluable help and comments in the preparation of this lecture. Righto. Well, we certainly live in exciting times. We'll see whether all of this actually lives up to the hype. I know. Lean Prover did find an interesting result, and it was novel, although it was a slight simplification of the problem that it set out to solve. So it got close. But Lean Prover definitely has like a robust language for it. All right, let's check out the benchmark. So FrontierMath, benchmarking AI against advanced mathematical research. Benchmark of several hundred unpublished expert-level mathematics problems that take specialists hours to days to solve. Difficulty tiers 1 to 3 cover undergraduate math through early graduate level problems. Tier 4 is research level mathematics. Right, so Claude 3.5 Sonnet in June 2024 had a 0% pass accuracy. And also in October. OpenAI's O3 Mini had a 4.17 pass accuracy. I don't know what any of these numbers really mean necessarily, so this isn't going to be particularly useful, but all right, 6.25 pass accuracy with 3.53% standard error. That's actually, a bit better. A bit better. even though the standard error was wider, right? It still covers the decent area. O3 high also in April 2025 got a 2.08% pass accuracy with 2.08 standard error. Oh, Grok 3 beta 0%. Claude Sonnet 4 0%. Claude Opus 4 4.17%. Gemini 2.5. Gemini 2.5 Pro. Grok 4, Gemini, GPT-5. This is all in August. Best one, 12.5 plus or minus 4.82. 12.5 plus or minus 4.8 in October was GPT-5. And then finally, Gemini 3, 18.75 plus or minus 5.69. So that's going to be a 13.06, kind of as the minimum level, provided that the standard error is reasonable to assume at this point. 9 correct out of 48. I would like to know which ones were like. That's not what I wanted. Okay, tier 1 through 3 results. So Gemini 3 Pro is almost outpacing at its lowest standard error, surpassing GPT-5 at its highest. Or lowest value based on highest error. And then GPT-5, highest value based on highest error. Gemini 3 answered 109 out of 290 correct on the tier 1 through 3 results. So that's mostly undergraduate stuff. I don't necessarily see that as impressive. I also do notice that lean is nowhere on this page. So, okay. Okay. Egg drop problems. They are cracked up to be. Kao Xiangwen, Chen Zhongyun, and Stephen J. Miller. Kangyi community in China. And Muang Chiang Mai district in Thailand. Department of Mathematics and Statistics at Williams College, Williamstown, Mass. For Dr. Miller. Okay. So, quite an interesting, like, cross-cultural exchange here. So we're getting some people from 3 different countries working together on trying to figure out how these egg drop problems are going to be useful in mathematics education. Okay. We explore higher dimensional generalizations of the classic egg drop problem, in which the goal is to create a critical breaking point using the fewest number of trials. Beginning with the one-dimensional case, we prove that k eggs and n floors, the minimal number of drops in worst case satisfies p1 of k is less than or equal to the ceiling k times capital N to the 1 over k. Okay. number of eggs times the number of floors raised to the 1 over k, 1 over number of eggs. The egg root. We then extend the recursive algorithm to 2 and 3 dimensions, proving similar formulas. P2 of k is less than or equal to k minus 1 times parentheses m plus n. Yep, I don't know what M and L are, but allegedly that should be the number of floors. But that's in a different direction. I'm not sure exactly where to go with that one. In 3D, a conjecture a general formula for the d-dimensional case. Beyond the critical point problems, we then study the critical line problems, where the breaking condition occurs along x plus y equals v, with a slope -1, or more generally, alpha x plus beta y equals v, slope unknown. Paper is an outgrowth of a talk given by the third named author, Stephen Miller, and attended by the first 2 authors at the Math League International Summer Tournament in Summer 25 in Trenton, New Jersey. It's a pleasure to thank the organizers, etc., etc., etc. Great. Y'all did an awesome job. Good. The egg drive problem is a classic puzzle that's fascinated mathematicians and computer scientists. It's often featured in technical reviews at major technology companies such as Microsoft and Google, as it elegantly combines combinatorial reasoning with dynamic programming techniques. Suppose we wish to know which windows in a 36-story building are safe to drop an egg from, and which will cause the egg to break on landing. Suppose 2 eggs are available. What is the least number of egg droppings that is guaranteed to work in all cases? Okay, an egg that survives the fall may be used again with no damage. Broken egg must be discarded. The effect of a fall is the same for all eggs. If an egg breaks when dropped, then it would break from a higher floor. If an egg survives a fall, then it would survive from a shorter fall and totally not be damaged from the initial impact. As said in the first one, it is not ruled out that the first floor break eggs, nor is it ruled out that a drop from the 36th floor does not cause an egg to break. Could be possible. Book displays optimal solution to the problem. Start at the 8th floor, and if the egg breaks, return to test every point from the first floor until the second egg breaks. Otherwise, use the first egg to test the 15th floor, and so on. No matter where the first egg breaks, it will always require no more than 8 drops. Right? So if this is going to make it to the 34th floor, for example, then they're saying go 8, 15, 21, 26, 30, 33, 35, 36 breaks, then the second egg automatically goes to 34 because we already tested 35. I don't know. 35, I don't know. 35 would break, therefore test 34 on the next one. Okay. 1, 2, 3, 4, 5, 7, 8. Yeah. Need a break before math. Oh. Brain is dopamine hungry. Yeah, it tends to do that. Okay, later, Boardman generalized this into the problem, given k eggs, how many floors can we handle if we have at most n drops? Using both generating functions and direct counting approach, he showed that the total number of floors that can be tested is the sum of the n choose j combinatorial number, where j goes from 1 to k. Building off Boardman's work, Parks and Wills extended the program using binary decision tree to calculate the most floors that can be explored with k eggs and d drops for 2 adaptive problems. So replacement eggs, the study of not study. The supply of eggs is restored to the original number k whenever that the egg that is dropped does not break. Bonus eggs. A new egg is received whenever the egg that is dropped does not break. All these results employ a dynamic search where each drop decision depends on previous outcomes. There's another family of methods known as statistical or fixed step strategies that we use in this paper. There are also many other adaptations that can be made. Paper builds on earlier lectures presented by third author in Math 331 at Williams College, as well as many math camps. We generalize the traditional egg drop problem into a problem with n floors, k eggs, and bound the optimal step size and least number of drops required under such a strategy. Beyond the one-dimensional problem, we also extend the traditional one-dimensional egg drop problem by introducing higher dimensional generalizations. Instead of searching a point along a vertical line of floors, we explore versions set in a two-dimensional plane and three-dimensional space, where the critical condition depends on multiple coordinates. Moreover, we continue this line of generalization to search for a critical line instead of a point in 2D plane. Okay, 2 and 3 critical point problem given here. Two-dimensional critical line x plus y equals v. Method 1. We perform a recursive jump search along the main diagonal of the rectangular region of dimensions m by n. For k greater than or equal to 1 eggs, the minimum number of drops required in the worst case scenario in method 1 must satisfy the following equations, or inequality, k times m plus n raised to the 1 over k. Two-dimensional critical line, method 2. We combine a diagonal search in the rectangular region of dimensions m by n with a final verification of the last uncertain point using the reserved egg. The minimum number of drops required in the worst case scenario under method 2 satisfies k minus 1 times m raised to the 1 over k minus 1. In future work, we plan to extend our study into... Oh man, this is a long one. I just noticed where the cursor was. Study of the two-dimensional critical line to the more general case, which introduces new challenges and strategies. We focused on minimizing the worst case number of drops, but would also consider minimizing the average case performance. Since the worst case only occurs rarely, it might be reasonable to allow some risk by optimizing the average instead. We do not address minimizing the average case in this paper, but leave it as direction for future research. Nice of you to do that. Section reviews a recursive strategy for one-dimensional egg drop problem. Distinct from this approach presented in the introduction, our method derives the optimal step size for the search and establishes upper bound on worst case number of drops. All results in this section prove by induction, and our one-dimensional search also serves as a foundation for the higher dimensional generalizations. Among a linear array of numbers 1 to n, there exists a unique critical point, 0 to capital N, where both n and capital N are integers, such that if a magical egg is dropped from any point a less than n, the egg remains intact with no damage, and if it is dropped from any point a greater than or equal to n, it breaks. We first describe the general strategy for solving this problem. If only one egg is available, test every lattice point from 1 upwards. If more than one egg is available, now we may introduce a different, more efficient searching approach. Suppose we have k eggs, n floors. Begin by dropping the egg at positions of the form I times s sub 1p k, where I is 1, 2, 3, etc. Here s sub 1p k denotes the k egg step size to be determined when performing the critical point search in the one-dimensional setting. Later we can similarly use s2p k and s3p k for critical point searches in higher dimensions, and s2l k for two-dimensional critical line search. Continue this process until the egg breaks at position t times s sub 1p k. Now we know that the critical point must lie on the interval given, which is now the red segment, consisting of exactly s sub 1p k candidate points, along which s sub 1p k minus 1 will need to be tested. Now we face a reduced subproblem, a k minus 1 egg search over a smaller interval of s sub 1p k 1 point, or minus 1 points. In the following recursive process, one egg is used to narrow down the interval. Then the same strategy is applied with the remaining k minus 1 eggs until only one egg is left. At this point, we revert to a linear search within the final subsegment. Base case, when k equals 1. Worst case scenario with only one egg. Egg does not break during sequential search until it is dropped at position n. Thus, step size must be 1, and number of drops required in the worst case is n. Base case holds since the optimal step size is given here, and n, which is 1. And the worst case number of drops is p sub 1 of 1, which gets us n. Inductive. Assuming that theorem 2.1 is true for k, must show that those are also true. To do so, we apply the recursive strategy described previously. Suppose we drop the egg at intervals of increment size s sub 1p k plus 1. Jump search from positions given here, stopping when the egg breaks. In the worst case, this requires n over s sub 1p k plus 1 drops with the first egg. Then we are left with a sub-interval, red subsegment of figure 2, that at most are s sub 1p k plus 1 minus 1 candidate points to search using the remaining k eggs. By the inductive hypothesis, the worst case number of drops needed to search a segment of size s sub 1p k plus 1 minus 1 with k eggs is at most k times s sub 1p k plus 1 minus 1 raised to the 1 over k, which is approximately equal to and less than k times s sub 1p k plus 1 raised to the 1 over k drops. Total number of drops in the worst case is given here. To minimize, we take the derivative and set it equal to 0. Get a critical point. This is a potential location for global maximum or minimum. Compute second derivative. Evaluating second derivative at critical point gets you the following, which verifies that the critical point is a local minimum. Since the domain is not an endpoint, the global minimum must occur either at this interior point, i.e. the critical point itself, or at an end point. Hey, Guitar Freak! Good evening and welcome. My name's Obi-Wan Pez. This is N Simplex Pachinko. Right now, we are reading a math paper called Egg Drop Problems. They are all they're cracked up to be. This was produced by 3 individuals who come from China, Thailand, and Williamstown, Massachusetts. And they were at a summer symposium trying to figure out some cool stuff that this is not like the physics egg drop problem where you try to like build a contraption to survive an egg, make an egg survive a fall. Rather, this is just taking a theoretical egg and tossing it out the window, and then if it doesn't break, you could just do it again, keep climbing until you do break it. Or they said if you want to optimize using the fewest number of eggs, how would you figure it out given a building that has, n floors? So we've been talking a little bit about how that's supposed to work. There was a process up here. If, for instance, there are 36 floors, and the first egg broke, and you only have 1 left, where do you test? So they said here, if it breaks, first egg breaks at floor 8, then you need to go back to the bottom and go 1, 2, 3, 4, 5, 6, 7 until it breaks somewhere in there. And that's how you know the highest floor that you could drop these eggs from. We're ignoring the fact that eggs are different from each other. And then similarly, if your first egg broke at floor 15, then you would go back to floor 9 and test up. So you went from there. So basically, if it passes at floor 8, you go to floor 15. If it passes at 15, you go to 21. If it passes at 21, you go to 26 to 30 to 33 to 35 to 36. If it passes all the way up, there you go. It made it 36 floors. Otherwise, any of these branches, it is a sorting algorithm, yes. Any of these branches that you take, you can always do it in no more than 8 drops. So no matter where you end up on this table, you can always get there in 8 drops. And again, that's 2 eggs. So they generalized for what happens when various things happen. And this is the kind of stuff that actually Zach and I have been talking about, especially, but in Peter Liljedahl's Building Thinking Classrooms, which is a book for mathematics educators who are interested in like a bit of a different teaching style. I'm going to be meeting with one of the math teachers at my kids' school after break. So once everybody comes back in January, we're going to sit down, and I wanted to actually go over the math curriculum of Britain. And then I was like, I've got this thing you might be interested in. So I gave him the elevator pitch, and he was like, that seems really interesting. I might buy the book. All right. Do not recommend for Christmas presents, by the way, unless you have like a math educator in the house. So, all right. By inductive process, worst case scenario is segment size with k eggs, at most this many, which is approximately equal to and less than this many drops. Total number of drops in the worst case is approximately this. To minimize, we calculate first derivative. Solving this for 0, we find the critical point. Boy, doesn't that look fun. This is a potential location for global minimum or maximum. Find the second derivative. We get this. It has to be greater than 0. It ended up with k plus 1 over k. So yeah, always positive. Proves that the critical point is a local minimum. Since the domain is this and not an endpoint, the global minimum must occur either at this interior point, the critical point itself, or an endpoint. As s sub 1p k plus 1 goes to 0 from the positive direction, we have all this stuff. This goes to infinity. This goes to 0. So therefore, f sub 1p k plus 1 of s sub 1p k plus 1 is going to positive infinity. Therefore, this function cannot have a global minimum. At this particular value is equal to n, we have the following, and this ends up getting 1 plus k times n to the 1 over k. At the critical point, we have the following. It's this. According to AMGM inequality, we have this greater than that. If we let all a's be equal to n to the 1 over k and a sub k plus 1 equal 1, then the arithmetic mean of these numbers is this right here. Geometric mean is the following. According to the inequality, we get this. Multiply both sides by k plus 1, yielding the following. If equality holds, no, the equality will hold if and only if n equals 1. In more general cases, i.e. n is greater than 1, this stuff implies that the function cannot achieve its goal of global minimum at the endpoint n. Okay. As illustrated by the knapsack problem, the integer minimum or maximum can significantly differ from its real value counterpart, so we need to be cautious when rounding. Yes. When we have 2 eggs, basic strategy, perform a linear search along each axis. Two-dimensional critical line. Okay. Right, so we could find candidate points for the second egg if we know where these critical or what happens at these individual critical lines. So it's looking like we want to test the outer critical lines first. The outer one coming up did not break, so we jumped to the highest. That one did break, and so we only have 2 more points that we need to test. At that point, it becomes linear again. So if we only have 2 eggs, then we want to go from the lower side up. Or if we want to minimize the number of broken eggs, start from the bottom and work your way up. Since we only have 2, right, pretty obvious what's going to happen. Either the first one breaks, and then therefore the original L1 was your highest that will survive, or L3 survives and L4 fails, at which point L3 is your best, or L4 also passes, in which case L4 becomes the best. Right, and again, more stuff here. Future work. Consider a rectangular region within the plane with coordinates ranging from 0, 0 to mn. Without loss of generality, assume m is greater than or equal to n. Within this region, there exists a unique critical line of the form alpha x plus beta y equals v that passes through the rectangle where x and y are variables. Alpha, beta, v are unknown constants with the following constraints. Critical line has a positive y-intercept. Slope of the critical line can be negative, 0, or undefined, so that the line can be descending, horizontal, or vertical. Critical line has to go through at least 2 lattice points on or within the boundary of the rectangle. Critical line determines the outcome of dropping a magical egg at point AB. If the point AB lies strictly below the line, the egg remains intact and undamaged, otherwise it will break. The objective is to split m plus 1 n plus 1 lattice points on and within the rectangle into 2 groups, safe and breaking. It's going to be impossible to complete this classification with only 1 egg, because we need at least 2 breaking points to narrow down the range and constrain the slope of the critical line. For example, egg breaks at 3, 0. There are 6 possible locations for the critical line, 2 of which are shown as L1, L2. Line enters 0, 1, exits 3, 0, or line enters 2, 2, and exits 3, 0. If L1 is a critical line, set save points to include 0, 0, 1, 0, 2, 0, and the rest are breaking. If L2 is the critical line, there are going to be 4 more save points. Thus, with only 1 egg, we cannot determine the complete set of breaking and non-breaking points. With only 2 eggs, we must use the most conservative approach to ensure that no lattice points on the critical line are skipped. First, perform a sequential search at every lattice point along the top and left sides of the rectangle using the first egg, and suppose that the egg breaks at a point 0a on the left side or bn on top. If the egg breaks at 0a, we must consider all points x, y within the boundary. If the egg breaks at bn, we can calculate the slopes from bn to every point x, y. Set of slopes is ordered in increasing value because a critical line must pass through at least 2 lattice points. Points share the same slope with respect to the first breaking point can be treated as a single candidate point. So yeah, anything along the radial coming from our critical point going out through every single point are all going to have the same break value. Oh man. So here with the 3-dimensional one, I think we got to use a plane in order to figure out all of it. But it's going to be the same sort of thing, I think. No. Maybe not. Analysis and comparison. Okay. Approximate. Leading term, natural log of 1 plus n over m, lies between 0 and natural log of 2. So about between 0 and 0.693. In correction terms, the difference between natural log of m plus n all squared and natural log of m squared is small, since the difference between natural log of m plus n and natural log m is natural log of 1 plus n over m, which is smaller than natural log 2. Okay. For small k, if 2 or 3 eggs are available, method 1 outperforms method 2. For large values of k, method 2 is slightly better, but the advantage is negligible. Overall, method 1 is the more efficient strategy. Okay. And I think we're going to leave it there because you probably heard my voice already tried to go. We are going to let's go visit Physics and Depression, who is doing some OpenStax College Physics, Chapter 23. I hope you all have a great day. Thank you so much for the follow. So we're going to go over and see Physics and Depression. Go check out his stream. And if anybody's looking for like physics help, Physics and Depression is one of our go-to people, as is Dr. Gold. A number of us also can do physics, but, most of us...
Shame.
Thank you, Famish.
Shame.
Most of us are mathematicians at heart, so, we're better at math, even if we can solve some physics problems. All right. Hope you all have a good day. I will be back tomorrow for... I will be back tomorrow for 9 Souls, where we are going to be doing some 100% cozy Tai Chi Kitty game. Totally. Not at all Dark Souls and, Dark Souls and Hollow Knight combined. So we'll be doing that tomorrow. And then on Wednesday, we're going to come back and do more cracking the GRE or, user questions, anything that anybody's interested in. So we'll see you all hopefully tomorrow. My name is Obi-Wan Pez. This is N Simplex Pachinko. We'll see you later.